When someone asks how far Voyager has traveled, most people expect a simple answer, a big number in kilometers or miles. But here's what makes Voyager's journey so fascinating. The distance isn't what you think it is. It's not straightforward. It's not just about how far the spacecraft has moved through space. There are layers to this question that reveal something profound about the universe itself. Understanding where Voyager really is and how we measure its journey will change how you think about distance, time, and what it means to explore the cosmos. If this sounds intriguing, a quick subscribe would mean the world to me, and let me know where you're watching from in the comments. Let's explore where Voyager really is. Let's start with what Voyager actually is. Voyager isn't one spacecraft, it's two, Voyager 1 and Voyager 2, twin spacecraft launched in 1977 by NASA. They're identical in design, both about the size of a small car, weighing about 8 gigaton, 125 kilograms each. Each carries a suite of scientific instruments, cameras for imaging, magnetometers for measuring magnetic fields, plasma detectors, cosmic ray sensors, instruments designed to study planets and the space between planets. They also each carry something remarkable, a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, music from different cultures, greetings in 55 languages, natural sounds like thunder and bird calls, images showing life on Earth, a message in a bottle sent to the cosmos. The mission was originally designed to last 5 years. Just 5 years. The goal was to visit Jupiter and Saturn, take pictures, gather data, and then the mission would be over. Nobody expected these spacecraft to still be functioning nearly 50 years later. But they are. They're still out there, still sending back data, still functioning far beyond anyone's expectations. This is a testament to the engineering and craftsmanship that went into building them. Every component was over-engineered. Every system had backups. The engineers who designed Voyager built them to survive the harsh environment of space for as long as physically possible, and it worked beyond their wildest projections. Voyager 1 launched on September 5, 1977. Voyager 2 actually launched first on August 20, 1977, but it was placed on a slower trajectory. The naming reflects the order they'd reach their destinations, not the order they launched. This is the first odd thing about the Voyager missions. Time and distance don't work quite the way you'd expect when you're dealing with spacecraft and planetary orbits. So, how far has Voyager actually traveled? The simple answer, the one you'll find if you look it up right now, is that Voyager 1 is about 24 billion kilometers from Earth. Voyager 2 is about 20 billion kilometers from Earth. These numbers increase every second. Every moment, the spacecraft move farther away. By the time you finish watching this, Voyager 1 will be hundreds of thousands of kilometers farther than when you started. In miles, Voyager 1 is about 15 billion miles from Earth. Voyager 2 is about 12.5 billion miles. These are the biggest distances humans have ever sent something. The farthest objects we've ever created. Nothing else we've built has traveled this far. To put this in perspective, light from Earth takes about 22 hours to reach Voyager 1. 22 hours. You send a radio signal to Voyager, it travels at the speed of light, and it takes almost a full day to get there. Then, when Voyager responds, that signal takes another 22 hours to come back. There's a 44-hour round-trip communication delay. If something goes wrong with Voyager, if an instrument fails or a system has a problem, the spacecraft has to handle it on its own. By the time we know there's an issue and send a command to fix it, nearly 2 days have passed. The situation might have changed completely in that time. The moon is about 1.3 light seconds away. The sun is about 8 light minutes away. Mars, at its closest, is about 3 light minutes away. Voyager 1 is 22 light hours away. Voyager 2 is about 18.5 light hours away. These spacecraft are so far out that we measure their distance in light hours, not light seconds or light minutes. They've left the realm of planets and entered the realm of interstellar space. They're in a place where normal planetary distances don't apply anymore. But here's where it gets complicated. When we say Voyager has traveled 24 billion kilometers, what does that mean? 24 billion kilometers from what? From Earth. Well, yes. Right now, Voyager 1 is about 24 billion kilometers from where Earth is right now. But Earth moves. Earth orbits the Sun at about 30 kilometers per second. Earth has moved billions of kilometers since Voyager launched. So is the distance measured from where Earth was when Voyager launched, or from where Earth is now? And does it matter? This is the problem with measuring cosmic distances. There's no fixed reference point. Everything in space is moving. Earth orbits the Sun. The Sun orbits the center of the Milky Way galaxy at about 230 kilometers per second. The galaxy itself is moving through space, pulled by the gravity of other galaxies. There's no such thing as standing still in space. There's no universal reference frame. All distances are relative to something else. So, when we measure Voyager's distance, we have to specify. Distance from what? Usually, when scientists give Voyager's distance, they mean distance from the Sun. The Sun is the center of our solar system, so it makes sense to use it as the reference point. Voyager 1 is about 24 billion kilometers from the Sun. That's about 161 astronomical units. An astronomical unit, or AU, is the average distance from Earth to the Sun, about 150 million kilometers. So, Voyager 1 is 161 times farther from the Sun than Earth is. Voyager 2 is about 134 AU from the Sun. These distances are increasing. Every year, Voyager 1 moves about another 3.5 AU farther from the Sun. Voyager 2 moves about 3.2 AU per year. They're not slowing down. There's nothing to slow them down. Space is essentially empty. There's no air resistance, no friction. The spacecraft coast through the vacuum at constant speed. Voyager 1 travels at about 17 kilometers per second relative to the Sun. Voyager 2 travels at about 15.4 kilometers per second. At these speeds, the spacecraft travel about 1 AU, the distance from Earth to the Sun, every single year. Think about that. The distance that took Apollo astronauts 3 days to cover when going to the Moon, which is much less than 1 AU, Voyager covers dozens of AU every year. The spacecraft travel at speeds that would get them from Earth to the Moon in less than 6 hours. If Voyager were heading toward Mars at its average distance, it would get there in about 4 days. If it were heading toward Jupiter at its average distance, it would take about a year and a half. But Voyager isn't heading toward Jupiter. It's heading out of the solar system, into interstellar space, into the vast darkness between stars. Now, let's talk about the path Voyager took to get where it is. The spacecraft didn't fly straight out from Earth. They couldn't. When they launched, they didn't have enough power to just blast away from the solar system. Rockets are limited by fuel. You can only carry so much fuel, and once it's burned, that's it. You coast at whatever speed you've achieved. To get the high speeds needed to leave the solar system, Voyager used a clever trick. Gravity assists. Planetary flybys that steal a tiny bit of orbital energy from the planets and add it to the spacecraft. Voyager 1's path went like this. Launch from Earth in September 1977, then fly through space for about a year and a half. In March 1979, Voyager reached Jupiter. It flew past Jupiter, taking incredible photographs of the planet and its moons. But the flyby wasn't just for pictures. As Voyager swooped past Jupiter, the planet's gravity pulled on the spacecraft. From Jupiter's perspective, Voyager fell toward it, swung around behind it, and then flew back out. But from the Sun's perspective, something interesting happened. Voyager picked up speed. It stole some of Jupiter's orbital momentum. Jupiter is so massive that it didn't notice the loss. But for Voyager, this gravity assist added several kilometers per second to its velocity. The spacecraft came in at one speed and left at a higher speed, all without burning any fuel. Then Voyager 1 continued to Saturn, arriving in November 1980. Another gravity assist. More incredible images. The rings of Saturn in detail never seen before. Moons with strange surfaces. Data that revolutionized our understanding of the outer planets. And another speed boost. After Saturn, Voyager 1 was done visiting planets. It had enough speed to leave the solar system entirely. It was on an escape trajectory. No more gravity wells to climb out of, just open space ahead. Voyager 2 took a different path. It also visited Jupiter and Saturn, but then it kept going. Because of the alignment of the planets in the late 1970s, a rare configuration that only happens once every 176 years, Voyager 2 could visit all 4 outer planets. Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, Neptune in August 1989. This was called the Grand Tour, 4 planets in one mission. Every flyby provided a gravity assist. Every encounter added speed. By the time Voyager 2 left Neptune, it was traveling fast enough to escape the Sun's gravity forever. Like its twin, it was heading for interstellar space. But here's the thing about this path. The distance Voyager traveled isn't a straight line from Earth to where it is now. The spacecraft flew in arcs. They swung around planets. They curved through space following the pull of gravity and the momentum they gained from each encounter. If you traced the actual path Voyager 1 took through space, it would be a complex curve. Earth to Jupiter, Jupiter to Saturn, Saturn onward and outward. The total distance traveled along this path is much longer than the straight line distance from Earth to Voyager's current position. Imagine you're driving across the country. You start in New York and you want to get to Los Angeles. If you could drive in a perfectly straight line, ignoring mountains and oceans and everything else, the distance would be about 4,000 kilometers. But you can't drive in a straight line. You have to follow roads. You have to go around obstacles. You stop in various cities along the way. The actual distance you drive might be 5,000 or 6,000 kilometers. The odometer in your car shows the distance you actually traveled, but the straight line distance from your starting point to your destination is less. Voyager is the same. The distance Voyager has traveled along its path is longer than the straight line distance from Earth to where it is now. So, which number matters? Both, depending on what you're asking. If you want to know how far Voyager is right now, the straight line distance is what matters. 24 billion kilometers. If you want to know how much distance the spacecraft has actually covered since it launched, you'd need to add up all the curves and arcs and planetary flybys. That number is higher, but usually when people ask how far Voyager has traveled, they mean how far away is it now? And the answer is 24 billion kilometers for Voyager 1, 20 billion for Voyager 2. Let's talk about speed in more detail. Voyager 1 travels at about 17 kilometers per second relative to the Sun. That's about 61,200 kilometers per hour, or about 38,000 miles per hour. At this speed, Voyager could circle the Earth in about 40 minutes. It could go from New York to Los Angeles in about 4 minutes. It's fast by any human standard. The fastest car ever built, the Thrust SSC, reached about 1,228 kilometers per hour. Voyager travels about 50 times faster than that. A commercial airliner cruises at about 900 kilometers per hour. Voyager is about 68 times faster. But here's the interesting thing. Despite traveling at these incredible speeds, Voyager isn't accelerating any more. It's not getting faster, it's coasting. And actually, very slowly, it's getting slower. Not because of friction or air resistance. Space is a vacuum, but because of the Sun's gravity. Even at 24 billion kilometers away, the Sun's gravity still pulls on Voyager. It's a tiny pull, almost negligible. But it's there. It's constantly trying to slow Voyager down, trying to pull it back. Voyager is climbing out of the Sun's gravitational well, and that climb costs energy. The spacecraft is slowly losing speed. The loss is tiny. Over the decades since Voyager left the planetary region, it's lost maybe a few meters per second of velocity. Not kilometers, meters. It's barely measurable, and Voyager is still traveling fast enough that it will never fall back. It has escape velocity. The Sun's gravity will never pull it back, but it will slow down, asymptotically approaching some final cruising speed as it gets farther and farther away and the Sun's gravity becomes weaker and weaker. There's also another factor. Voyager is moving through space, but space isn't perfectly empty. There's the interstellar medium, the thin gas that fills the space between stars. It's incredibly thin, about 1 atom per cubic centimeter on average. For comparison, the air you're breathing has about 10 to the 19th atoms per cubic centimeter. The interstellar medium is a trillion times less dense than air. It's essentially a vacuum by any standard. But over billions of kilometers, even this thin medium creates a tiny amount of drag. Not much. Not enough to slow Voyager noticeably in a human lifetime, but over millions of years, it matters. Eventually, far in the future, this drag will slow Voyager down. Not stop it, but slow it to the average speed of the interstellar medium itself. Let's put Voyager's speed in another context. Light travels at about 300,000 kilometers per second. Voyager travels at about 17 kilometers per second. That means Voyager is traveling at about 0.0057% the speed of light. About 1/17,000th the speed of light. Light can travel from Earth to Voyager in 22 hours. Voyager, traveling at its current speed, would take about 73,000 years to travel the same distance. This shows you the vast difference between even our fastest spacecraft and the speed of light. If Voyager were heading toward the nearest star, Proxima Centauri, which is about 4.2 light-years away, it would take about 73,000 years to get there at its current speed. 73,000 years? Modern humans have only existed for about 300,000 years. Civilization has only existed for about 10,000 years. Voyager would need more time than all of recorded human history to reach even the nearest star. And that's assuming Voyager doesn't slow down and assuming it were heading in the right direction, which it's not. Proxima Centauri is in a completely different direction from where Voyager is heading. So, where is Voyager heading? Voyager 1 is heading roughly in the direction of the constellation Ophiuchus. In about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 445. 1.6 light-years is still an enormous distance, about 10 trillion kilometers. Voyager won't be close enough to feel any significant gravitational pull from the star. It'll just drift past in the darkness, and after that, it will continue on, drifting through the galaxy, an artificial object, a creation of humans traveling through space essentially forever. Voyager 2 is heading in a different direction, toward the constellation Sagittarius. In about 40,000 years, it will pass near a star called Ross 248. Again, not close enough to interact, just passing through the same general region of space. Both spacecraft are on trajectories that will take them out of the solar system and into the galaxy proper. They'll orbit the center of the Milky Way galaxy along with all the other stars, including our Sun. They'll make one orbit every 225 million years or so. The Sun does the same. We're all orbiting the galactic center together. Voyager has just left the Sun's immediate neighborhood and joined the broader galactic community. One of the most significant milestones in Voyager's journey was crossing the heliopause. The heliopause is the boundary where the Sun's influence ends and interstellar space begins. The Sun constantly emits the solar wind, a stream of charged particles that flows outward in all directions. This solar wind creates a bubble around the Sun called the heliosphere. Inside the heliosphere, the solar wind dominates. Outside the heliosphere, the interstellar medium dominates. The boundary between them is the heliopause. Voyager 1 crossed the heliopause on August 25, 2012. It became the first human-made object to enter interstellar space. The crossing wasn't sudden. The boundary isn't sharp like a wall. It's a transition region where the solar wind slows down and mingles with the interstellar medium. Over several months, Voyager 1's instruments detected changes. The density of solar wind particles decreased. The density of cosmic rays from outside the solar system increased. The magnetic field changed direction. All of these signs pointed to the same conclusion. Voyager had left the heliosphere. It was in interstellar space. Voyager 2 crossed the heliopause on November 5, 2018. Again, instruments detected the telltale signs: the decrease in solar wind particles, the increase in cosmic rays, the change in magnetic field. Both spacecraft have now left the Sun's immediate domain and entered the space between stars. This is a historic achievement. Humans have sent objects into interstellar space, not far into interstellar space. The nearest stars are still tens of thousands of years away at Voyager's speed, but we've crossed the boundary. We've left our star's neighborhood. What does this mean? It means Voyager is now in an environment dominated by the galaxy rather than by the Sun. The particles Voyager detects are mostly from interstellar space, not from the Sun. The magnetic field it measures is the magnetic field of the local interstellar medium, shaped by the galaxy and by nearby stars. Voyager is sampling the space that lies between stars, the same space that future interstellar missions will have to cross, the same space that separates us from our stellar neighbors. And it's giving us data, information about what interstellar space is actually like: the density, the temperature, the magnetic field, the cosmic ray environment. All of this is new data, things we couldn't know without actually sending a probe there. But Voyager is still technically in the solar system in one sense. The solar system isn't just the planets. It also includes the Oort cloud, a vast spherical shell of icy bodies that extends far beyond the planets. The Oort cloud is thought to start at about 2,000 AU from the Sun and extend to maybe 100,000 AU or more. Voyager, at 160 AU, hasn't even begun to enter the Oort cloud. It will take about 300 years for Voyager to reach the inner edge of the Oort cloud, and it will take about 30,000 years to pass completely through it and emerge on the other side. So, while Voyager has left the heliosphere and entered interstellar space, it's still within the most distant reaches of the Sun's gravitational influence. This brings up an interesting question. When does something truly leave the solar system? Is it when it crosses the heliopause? Is it when it passes through the Oort cloud? Is it when the Sun's gravity becomes weaker than the gravity of other nearby stars? There's no single answer. It depends on what you mean by solar system. But for practical purposes, crossing the heliopause is considered leaving the solar system. Voyager is in interstellar space. It's farther from the Sun than any human-made object has ever been. And it's still going. The fact that Voyager is still functioning is extraordinary. The spacecraft were designed to last 5 years. They've lasted nearly 50. They're powered by radioisotope thermoelectric generators, or RTGs. These devices use the heat from decaying plutonium-238 to generate electricity. When Voyager launched, the RTGs produced about 470 watts of power. Now, Nearly 50 years later, they produce about 240 watts. The plutonium decays over time, releasing less heat, and the thermocouples that convert heat to electricity degrade. Every year, Voyager loses about 4 watts of power. This slow decline is inevitable. Eventually, there won't be enough power to run the instruments. Then there won't be enough power to run the transmitter, and Voyager will go silent. We'll lose contact. The spacecraft will continue drifting through space, but we won't hear from it anymore. NASA estimates that Voyager will have enough power to operate at least one instrument until about 2025. Maybe a bit longer if they're lucky. After that, difficult choices will have to be made. Which instruments to shut down to conserve power for the others? How to balance scientific return against the desire to keep the spacecraft communicating as long as possible. Eventually, probably sometime in the early 2030s, the power will drop below the level needed to run the transmitter. Voyager will send its last signal, and then silence. After that, Voyager will be on its own. A derelict spacecraft, no longer functioning, drifting through the galaxy. But even then, its journey won't be over. It will keep moving. It will pass near other stars tens of thousands of years from now. It will orbit the galaxy for billions of years. It might even outlast Earth. In about 5 billion years, the Sun will expand into a red giant and likely engulf Earth. But Voyager, far from the Sun, will be unaffected. It will keep drifting, a monument to human exploration, a time capsule from the 20th century, traveling through space essentially forever. The distance Voyager has traveled also raises interesting questions about the nature of measurement itself. When we say something is 24 billion kilometers away, we're assuming space itself is static. But space isn't static. Space is expanding. The universe is expanding. On the scale of the solar system, this expansion is tiny, negligible, unmeasurable. But it's real, and over vast distances, it matters. Between galaxies separated by billions of light years, space expands fast enough that the galaxies move apart faster than light can travel between them. Does this affect Voyager? Not measurably. The Sun's gravity binds the solar system together strongly enough that local expansion of space doesn't affect the distances between objects in the solar system. But it's a reminder that even the concept of distance is more complicated than it seems. There's also the question of reference frames. Relativity tells us that there's no absolute frame of reference. All motion is relative. Voyager is moving at 17 kilometers per second relative to the Sun. But relative to the center of the galaxy, Voyager has a different velocity. The Sun orbits the galactic center at about 230 kilometers per second. Voyager shares this motion plus its own motion relative to the Sun. So, relative to the galactic center, Voyager's velocity is some combination of these two velocities, depending on the direction it's heading. And relative to other galaxies, the velocity is different again because our galaxy itself is moving through space. There's no single true velocity for Voyager. It depends on what you're measuring against. This is one of the insights of special relativity. Velocity is always relative to something else. There's no cosmic speedometer that tells you your absolute speed. only your speed relative to other objects. For practical purposes, we measure Voyager's distance and velocity relative to the Sun because that's the most useful frame of reference for understanding its mission and its location in the solar system. But it's worth remembering that this is a choice, a convention, not an absolute truth. Let's think more carefully about what it means to be in interstellar space. The term sounds romantic, evocative, the space between stars. But what is it actually like? It's not empty. Space is never truly empty. Even in the vast reaches between stars, there's matter. About 1 atom per cubic centimeter, as I mentioned, mostly hydrogen, some helium, trace amounts of heavier elements. These atoms form a thin gas, the interstellar medium. In some regions, the density is higher, maybe tens or hundreds of atoms per cubic centimeter. In molecular clouds, where stars form, the density can reach millions of atoms per cubic centimeter. In other regions, in the hot ionized gas between spiral arms, the density might be only 0.1 atoms per cubic centimeter or less. Voyager is currently traveling through the local interstellar cloud, a relatively dense region by interstellar standards with about 0.3 atoms per cubic centimeter. This cloud is part of a larger structure called the local bubble, a region about 300 light-years across, where the interstellar medium is hotter and less dense than average. The local bubble was likely carved out by supernova explosions over the past 10 to 20 million years. The shock waves from these explosions swept up the gas, compressing it at the edges and leaving a bubble of hot, thin gas in the middle. Our solar system happens to be inside this bubble, and Voyager, now outside the heliosphere, is measuring the properties of the local bubble directly. What else is in interstellar space? Magnetic fields. The galaxy has a magnetic field, though it's weak, about 6 microgauss. That's about 1,000,000 times weaker than Earth's magnetic field. But over vast distances, these weak magnetic fields can channel the flow of charged particles, shaping the structure of the interstellar medium. Cosmic rays, high-energy particles, mostly protons, that zip through space at nearly the speed of light. They're called cosmic rays, but they're actually particles, not rays. They were named before anyone understood what they were. These cosmic rays are produced by supernova explosions, by pulsars, by active galactic nuclei. They travel through the galaxy, bouncing off magnetic fields, creating a diffuse background of high-energy radiation. Voyager measures cosmic rays. Inside the heliosphere, the solar wind partially shields the inner solar system from cosmic rays. The wind creates a magnetic barrier that deflects some of the cosmic rays. But once Voyager crossed the heliopause, the cosmic ray intensity increased. Voyager is now exposed to the full cosmic ray environment of interstellar space. This data tells us about the sources of cosmic rays, about how they propagate through the galaxy, about the magnetic structure of the local interstellar medium. There's also dust, tiny grains of solid material, silicates, carbon, ices. These grains are microscopic, much smaller than a grain of sand, but they're everywhere. Over vast distances, they add up. They block and scatter light, creating the dark lanes we see in images of galaxies. They're also where much of the chemistry of space happens. Molecules form on the surfaces of dust grains, complex organic molecules. Amino acids, the building blocks of life. Interstellar space isn't just empty void. It's a rich chemical environment where the raw materials for planets and life are created and dispersed. Voyager doesn't directly detect dust grains. It's moving too fast. A dust grain hitting Voyager at 17 kilometers per second would be like a bullet impact. It could damage or destroy the spacecraft. But Voyager does carry a detector for dust grain impacts, a simple device that measures the tiny electrical signals created when a grain hits and vaporizes. Over the decades, this detector has recorded occasional impacts, giving us some information about the density and size distribution of dust in the outer solar system and near interstellar space. Now let's consider the human side of Voyager's journey. The distance Voyager has traveled isn't just a number. It represents decades of human effort. Engineers, scientists, mission controllers, people who have dedicated their careers to keeping these spacecraft running. When Voyager launched in 1977, the people running the mission were in their 20s and 30s. Now they're in their 60s and 70s. Some have retired, some have passed away, but the mission continues. New people join the team, learn the systems, take over responsibilities. It's a multi-generational effort now. The people currently working on Voyager weren't born when the spacecraft launched. They grew up in a world where Voyager was already out there, already exploring, already sending back data. The team is small now. Only about a dozen people work directly on Voyager operations. Compare that to current missions like the James Webb Space Telescope or the Perseverance rover, which have teams of hundreds or thousands. Voyager is old. Its technology is ancient by modern standards. It has less computing power than a modern smartphone. Its data rate, the speed at which it sends information back to Earth, is about 160 bits per second. That's slower than the modems people used to connect to the internet in the 1990s. A single image from Voyager's cameras, if they were still working, would take hours to transmit. Sending the kind of high-resolution images we get from Mars, rovers would take weeks or months. But Voyager doesn't need to send images anymore. The cameras were turned off decades ago to save power. Now Voyager sends data from its remaining instruments. Particle detectors, magnetometers, the plasma wave instrument, simple measurements, particle counts, magnetic field strength and direction, plasma wave frequencies. Each measurement is just a few numbers, but those numbers tell us about the environment Voyager is passing through. They tell us what interstellar space is like, and they're data we can't get any other way. No telescope on Earth or in orbit can measure what Voyager measures. You have to be there. You have to send a probe into interstellar space and measure directly. The communication itself is remarkable. Voyager transmits at 20 watts. That's about the power of a refrigerator light bulb. 20 watts of radio power sent from 24 billion kilometers away, spreading out in all directions as it travels. By the time the guide signal reaches Earth, it's incredibly weak. About 10 to the minus 16 watts per square meter. That's 0.00000000000001 watts per square meter. It's one of the weakest signals humans regularly detect. To catch this faint whisper from across the solar system, NASA uses the Deep Space Network, a collection of giant radio antennas located in California, Spain, and Australia. Each antenna is 70 meters across, about the size of a large house. These enormous dishes focus on Voyager for hours, carefully amplifying the signal, filtering out noise, extracting the data bit by bit. And it works. We still hear Voyager, loud and clear by astronomical standards. The signal is clean. The data is good, but every year, as Voyager moves farther away, the signal gets a little weaker. The inverse square law is relentless. Double the distance, the signal strength drops to 1/4. Triple the distance, it drops to 1/9. Voyager is 10 times farther from Earth than it was when it visited Saturn. The signal is 100 times weaker than it was back then, and it's still detectable. But there will come a time when the signal is too weak even for the Deep Space Network. Not yet, not for years or decades, but eventually. When that happens, we'll lose contact, even if Voyager still has power. The spacecraft will be talking, but we won't be able to hear it anymore. There's something poignant about that. Voyager will outlive our ability to communicate with it. For a while, maybe decades, the spacecraft will be functional but unreachable, still out there, still operating, still measuring and recording data that no one will ever see. And then, when the power finally runs out, Voyager will fall silent. The instruments will stop, the transmitter will stop, the thermal control systems will stop. The spacecraft will start to freeze. Without power, without heaters, Voyager's internal temperature will drop to match the temperature of space. About 3 Kelvin, 3 degrees above absolute zero. Everything will freeze solid. The electronics, the fuel lines, the instruments. Voyager will become a frozen relic, a piece of space archaeology, an artifact from Earth's first attempt to explore beyond the solar system. But the golden record will remain. Mounted on the side of each spacecraft is that 12-inch gold-plated disc, the sounds and images of Earth. Greetings from the people of our world. Music from Bach, Beethoven, Chuck Berry, traditional songs from around the globe. Sounds of thunder, wind, surf, birds, whales. Images of humans, animals, landscapes, cities. Diagrams showing Earth's location relative to pulsars. Instructions for playing the record etched onto the cover. A time capsule, a message in a bottle. Carl Sagan, who led the committee that created the record, called it an expression of hope. A hope that someone, someday, might find Voyager, might recover it, might decipher the record, might learn that we existed, that we sent this message, that we reached out across the cosmos to say hello. The odds of this happening are vanishingly small. Space is vast. Voyager is tiny. A spacecraft 8 meters across, adrift in a galaxy 100,000 light-years wide. The chances of another civilization finding it are essentially zero. Even if intelligent life is common in the galaxy, even if there are millions of civilizations out there, the volume of space is so large that the probability of any of them stumbling across Voyager is negligible. Voyager won't pass close to another star for tens of thousands of years. And even then, close means more than a light year away. A spacecraft passing a light year from a star would be invisible, undetectable. It would drift past, unseen, unnoticed, so the golden record probably won't be found, probably won't be played, probably won't deliver its message. But that's not really the point. The point is that we tried. We sent the message. We put our best foot forward. We said, this is who we are. This is what we value. This is our planet, our species, our music, our words. We're here in this corner of the galaxy, on this small world orbiting an ordinary star. And we reached out. We sent our voice into the cosmos, not knowing if anyone would hear, not expecting anyone to hear, but hoping, always hoping. The distance Voyager has traveled, those 24 billion kilometers, represents more than just distance. It represents human curiosity, the drive to explore, the need to see what's beyond the next hill, the next ocean, the next planet. We're explorers by nature. It's in our biology, our evolution. The ancestors who stayed home, who never ventured beyond their immediate surroundings, were less successful than those who explored, who migrated, who discovered new lands and new resources. Exploration is part of who we are, and Voyager is an expression of that. An exploration beyond Earth, beyond the moon, beyond the planets, into the space between stars, into the unknown. Every kilometer Voyager travels is a kilometer no human-made object has ever traveled before. Every day, Voyager sets a new record for the most distant object from Earth. Every second, it's farther away than it was the second before. This record will stand for a long time. No current mission will surpass Voyager's distance within our lifetimes. The New Horizons spacecraft, which flew past Pluto in 2015, is also heading out of the solar system. But it's traveling slower than Voyager and will take longer to reach the same distances. Eventually, decades from now, New Horizons might overtake Voyager 2. But Voyager 1, traveling faster than any other spacecraft, will likely remain the most distant human object for the foreseeable future, unless we build something faster, unless we develop new propulsion systems, nuclear propulsion, ion drives, solar sails, breakthrough starshot, the proposal to send tiny spacecraft to Alpha Centauri using powerful lasers could create probes that travel at 20% the speed of light. If that works, those probes would pass Voyager in a matter of days or weeks. They'd reach in years what it takes Voyager tens of thousands of years to reach. But that technology doesn't exist yet. It's theoretical, unproven. Maybe it will work, maybe it won't. For now, Voyager holds the record, the farthest traveler, the most distant emissary, and there's something fitting about that. Voyager wasn't designed to break records. It was designed to study Jupiter and Saturn. The fact that it's still going, still exploring, still sending data nearly 50 years later is a bonus, an unexpected gift. The mission succeeded beyond all expectations. And now Voyager serves a different role. It's a pioneer, a pathfinder. It's showing us what lies beyond the planets, what interstellar space looks like, what conditions a future interstellar probe would encounter. It's gathering data that will inform the design of the next generation of exploration missions. The lessons learned from Voyager about spacecraft longevity, about communication over vast distances, about operating in extreme environments will guide future missions. Voyager is the trailblazer, and everything that follows builds on what Voyager has done. Let's think more deeply about what Voyager's distance means in practical terms. 24 billion kilometers. It's a number so large, it loses meaning. Our brains aren't built to comprehend distances like this. So let's break it down. Let's build intuition step by step. Start with something familiar, the distance from your house to the nearest store. Maybe a kilometer, maybe 5 kilometers. You can walk or drive this distance easily. Now, scale up. The distance across your country. For the United States, coast to coast, about 4,500 kilometers. You can drive this in a few days. You can fly it in 5 hours. It's large, but comprehensible. You can imagine the journey. Now scale up again. The distance around the Earth. About 40,000 kilometers. Early explorers took years to sail this distance. Modern aircraft can do it in 2 days with stops for refueling. It's the largest distance that's still tied to Earth, still within our immediate experience. Now, let's leave Earth. The Moon is about 384,000 kilometers away, about 10 times the distance around Earth. Apollo astronauts took 3 days to get there. At highway speeds, driving non-stop, it would take about 6 months. The Moon is far, but it's still close enough that we can see it, photograph it, send humans there and bring them back. The Sun is about 150 million kilometers away, about 400 times farther than the Moon. Light takes 8 minutes to travel from the Sun to Earth. At highway speeds, you'd need about 170 years of continuous driving to reach the Sun's distance. No human has ever been this far from Earth. The farthest humans have been is the Moon. Everything beyond the Moon is territory explored only by robotic spacecraft. Mars, at its closest, is about 55 million kilometers away, about 1/3 the distance to the Sun. Spacecraft take about 6 to 9 months to reach Mars. At highway speeds, you'd need about 60 years to drive the distance to Mars. Jupiter, at its closest, is about 630 million kilometers away. Voyager took about 18 months to reach Jupiter from Earth. At highway speeds, you'd need about 700 years. Saturn is about 1.2 billion kilometers at its closest. Voyager took about 3 years to reach Saturn from Jupiter. At highway speeds, you'd need about 1,300 years to drive to Saturn. By now, we're in distances where highway speeds are meaningless. The numbers become abstract. 1,000 years of driving to reach Saturn. It's incomprehensible. Neptune, the outermost planet, is about 4.5 billion kilometers from the Sun. Voyager 2 took 12 years to reach Neptune from Earth. At highway speeds, you'd need about 5,000 years. All of recorded human history is about 5,000 years old. You'd need to drive since the invention of writing to reach Neptune. And Voyager is now 24 billion kilometers from the Sun, about 5 times the distance to Neptune. At highway speeds, you'd need about 25,000 years. That's more than twice as long as recorded history. If you started driving when humans first invented agriculture and began settling in permanent communities, you'd still be driving today. You wouldn't be there yet. You'd still have thousands of years to go. That's how far Voyager has traveled. a distance that makes Neptune, the farthest planet, seem close by comparison, a distance that reduces the orbits of all the planets to a tiny region around the Sun. From Voyager's perspective, the solar system looks very different than it does from Earth. From Earth, the solar system seems vast. The planets are spread across billions of kilometers. Each one occupies a distinct orbital radius. There's space between them, huge, empty space. But from Voyager's perspective, the planets are all clustered together near the Sun. All the planets, from Mercury to Neptune, orbit within 30 AU of the Sun. Voyager is at 160 AU. From out there, looking back, all the planets are within a tiny region. They're all basically in the same place, huddled around the Sun. The differences in their orbital radii, which seem so significant from Earth, are tiny from Voyager's vantage point. If you could see the solar system from Voyager's position, which you can't because the planets are too dim and too small at that distance, but if you could, you'd see the Sun as a bright star, brighter than any other star in the sky, but still just a star, not the overwhelming disk we see from Earth. And clustered around this bright star, too close to resolve individually without a telescope, you'd see the planets, Earth, Venus, Jupiter, all of them compressed into a small angular region, the solar system as a whole, the system of planets orbiting the Sun. From this perspective, you'd see it as a complete structure, something you can't do from Earth because we're inside it. This external view is valuable scientifically. It gives us perspective on our place in the universe. The solar system, which seems so large and significant from inside, is actually tiny, just a small collection of planets around an ordinary star. There are hundreds of billions of stars in our galaxy. Most of them probably have planets. The solar system is just one system among countless others. Voyager, by traveling beyond the planets, by seeing the system from outside, reminds us of this. We're not at the center of anything special. We're just one small system in a vast galaxy. Voyager's journey puts us in our place, cosmically speaking, but there's also something uplifting about this perspective. Yes, we're small. Yes, we're insignificant in cosmic terms, but we're also capable. We built something that could travel this far. We sent a spacecraft beyond the planets into interstellar space, and we're still in communication with it. We're monitoring its journey in real time. We're receiving data from a place no human will visit in our lifetimes, maybe not in many lifetimes. That's an achievement, a profound achievement. It shows what humans can do when we work together toward a common goal. When we dedicate resources and knowledge and effort to exploration and discovery. Voyager's distance is also a reminder of time. The spacecraft has been traveling for nearly 50 years. Most people alive today weren't born when Voyager launched. For them, Voyager has always been out there, always exploring, always distant. For older people, those who remember the launches in 1977 Voyager, represents a lifetime. They've lived their entire adult lives with Voyager in space. They've seen the mission evolve from a planetary exploration mission to an interstellar mission. They've watched the science unfold, the discoveries at Jupiter, the rings of Saturn revealed in stunning detail, Uranus and Neptune visited for the first and only time, the crossing of the heliopause, the entry into interstellar space, all of this unfolding over decades. Time and distance are connected in space exploration in a unique way. On Earth, you can travel large distances quickly. You can fly from New York to Tokyo in about 14 hours. But in space, even our fastest spacecraft travel slowly compared to the distances involved. Voyager travels at 17 kilometers per second, incredibly fast by human standards, but it still takes decades to cover interplanetary distances and tens of thousands of years to cover interstellar distances. This creates a strange situation where space missions outlast careers, outlast lifetimes. The people who planned Voyager's mission to Jupiter and Saturn are now retired or gone. The spacecraft outlived them. The mission is now in the hands of a new generation, people who inherited it from the previous generation. And, eventually, this generation will pass it on to the next, if Voyager lasts that long. This multi-generational aspect of space exploration is something we'll have to get used to if we want to explore beyond the solar system. Interstellar missions will take centuries or millennia. No one who launches the mission will live to see it arrive. The mission will pass from generation to generation, parents telling children about the distant probe, children growing up and becoming the mission controllers and scientists, eventually telling their own children. The mission becomes part of the culture, part of the shared story. Voyager is the first hint of this, the first mission that spans multiple generations. And it shows us that it's possible, that we can maintain continuity over decades, that missions don't have to be completed in a single lifetime to be worthwhile. The trajectory Voyager follows is also worth contemplating. It's not a straight line. Nothing in space moves in straight lines. Gravity curves all paths. Voyager's path is a hyperbola relative to the Sun, a conic section. The spacecraft approached the Sun, reached perihelion, the closest point to the Sun, during its journey through the planetary region, and now it's receding. The path curves away from the Sun, asymptotically approaching a straight line, but never quite reaching it. Over billions of kilometers, the Sun's gravity still curves Voyager's trajectory just slightly, just measurably. This curve is evidence of gravity's infinite range. The force gets weaker with distance, but never drops to zero. It's always there, always pulling, even if only infinitesimally. From a galactic perspective, Voyager's trajectory is even more complex. The Sun orbits the galactic center and Voyager moves with it, sharing this orbital motion. But Voyager also has motion relative to the Sun. The combination creates a helical path through the galaxy, a spiral, like a thread wrapped around a moving cylinder. Voyager spirals through galactic space, following the Sun's orbit, but also moving outward relative to the Sun. Over millions of years, as the Sun completes its orbit around the galaxy, Voyager will trace out this spiral, moving farther and farther from the Sun's immediate vicinity, but always remaining gravitationally bound to the galaxy as a whole, orbiting the galactic center just like any other star. The way we track Voyager's position is a remarkable feat of engineering and precision. We can't see Voyager. Even with the most powerful telescopes, the spacecraft is too small and too far away to image directly. Instead, we track it using radio signals. Voyager transmits continuously on two frequencies, a primary frequency and a backup. These signals travel at the speed of light back to Earth. When they arrive, the Deep Space Network antennas detect them, but detecting the signal is only the first step. We also need to measure it. Specifically, we need to measure the Doppler shift. The Doppler shift is a change in frequency caused by motion. You're familiar with this effect from everyday life. When an ambulance approaches you, its siren sounds higher pitched than when it's stationary. As it passes and moves away, the siren sounds lower pitched. The sound waves are compressed as the ambulance approaches, making the frequency higher, and stretched as it recedes, making the frequency lower. Light and radio waves do the same thing. If a source is moving toward you, the waves are compressed and the frequency increases. If it's moving away, the waves are stretched and the frequency decreases. Voyager is moving away from Earth at about 17 kilometers per second. This motion causes its radio signal to be Doppler, shifted to a lower frequency. By measuring the exact frequency of the signal and comparing it to the frequency Voyager is transmitting, we can calculate how fast Voyager is moving away from us. The measurement is incredibly precise. We can detect velocity changes of fractions of a millimeter per second. This allows us to track Voyager's motion with extraordinary accuracy. We know where it is, how fast it's moving, and which direction it's heading to within very tight tolerances. But there's a complication. Earth rotates. Earth orbits the Sun. The Deep Space Network antennas are on Earth's surface, so they're moving too. To accurately measure Voyager's velocity, we have to account for the motion of the antenna. We have to subtract Earth's rotation and Earth's orbital motion from the measurement. This requires knowing Earth's motion very precisely, which we do. We've measured Earth's orbit and rotation to extraordinary precision using satellites, laser ranging to the moon, and other techniques. With this information, we can untangle Voyager's motion from Earth's motion and determine Voyager's true velocity relative to the Sun. There's also the issue of signal delay. When we receive a signal from Voyager, it was transmitted 22 hours ago. The signal we're receiving right now left Voyager yesterday. By the time we process the signal and determine Voyager's position and velocity, that information is already out of date. Voyager has moved since then. At 17 kilometers per second, Voyager travels about 1.5 million kilometers per day. So the position we calculate is always about 1.5 million kilometers behind where Voyager actually is right now. For most purposes, this doesn't matter. We're tracking trends over weeks and months, not seconds. But it's a reminder that there's no instantaneous knowledge of Voyager's location. Everything we know is delayed by the light travel time. Another way we track Voyager is by measuring the signal's travel time directly. We can send a command to Voyager and measure how long it takes for the response to arrive. Since the signal travels at the speed of light, the round-trip time tells us the distance. If the round trip is 44 hours, Voyager is 22 light hours away. Simple in principle, but complicated in practice because we have to account for the fact that both Voyager and Earth are moving during those 44 hours. The positions changed between when the command was sent and when the response arrived. But With careful calculations, we can work out the distance. These tracking techniques give us Voyager's position to within a few kilometers. A few kilometers out of 24 billion. That's precision of about 1 part in 10 billion. It's like measuring the distance across the United States to within millimeters. This precision is necessary because we need to know exactly where Voyager is to understand the data it's sending. If Voyager detects a change in particle density or magnetic field strength, we need to know where that measurement was taken so we can map the structure of the interstellar medium. Over time, as Voyager moves through different regions of space, it's building up a map. A one-dimensional map, a line through space, but a map nonetheless. And that map is valuable because we have no other way to get this information. Let's talk about what Voyager has discovered. The list is long. At Jupiter, Voyager found active volcanoes on the moon Io. This was a surprise. Before Voyager, no one knew there was active volcanism anywhere in the solar system except Earth. Io's volcanoes eject sulfur and sulfur dioxide high above the surface, creating a torus of material around Jupiter. Voyager also discovered Jupiter's rings, faint and dusty, nothing like Saturn's magnificent rings, but rings nonetheless. And it measured Jupiter's magnetic field, found lightning in the atmosphere, and observed the complex swirling storms that characterize the planet's cloud layers. At Saturn, Voyager revealed the rings in unprecedented detail. The rings aren't solid. They're made of countless individual particles, ranging from dust grains to boulders, all orbiting Saturn independently. The rings have structure, gaps and divisions. The Cassini division, a large gap in the rings. The Encke gap, ringlets and braids and spokes, transient features that come and go. Voyager also discovered new moons, small irregular moons embedded in the rings or orbiting just outside them. And it studied Titan, Saturn's largest moon, finding a thick atmosphere made mostly of nitrogen. Titan was intriguing, but Voyager couldn't see the surface through the haze. That would have to wait for the Cassini mission decades later. Voyager 2 continued to Uranus, arriving in January 1986. Uranus was a mystery before Voyager. Ground-based telescopes could see it as a small blue-green disk, but details were impossible to resolve. Voyager found a planet tipped on its side. Uranus's rotation axis is tilted 98 degrees from its orbital plane. Essentially, the planet rolls along its orbit rather than spinning upright like the other planets. Why? No one knows for certain. Likely a giant impact early in the solar system's history knocked Uranus over. Voyager also found Uranus's magnetic field, which is tilted 60 degrees from the rotation axis and offset from the planet's center. A strange configuration, and it discovered 10 new moons and studied the planet's faint rings. Then Neptune in August 1989. Neptune was expected to be bland, a blue ice giant with little going on. But Voyager found a dynamic atmosphere with high-speed winds, the fastest in the solar system, reaching 2,000 kilometers per hour. There was the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot. There were white clouds, methane ice crystals floating high in the atmosphere. And there was Triton, Neptune's largest moon, which turned out to be one of the most interesting objects in the solar system. Triton is captured. It orbits Neptune backward, opposite to Neptune's rotation, which means it didn't form with Neptune, but was captured later. And Triton has geysers, nitrogen geysers, plumes of nitrogen gas erupting from the surface and carried by winds across the icy plains. Active geology on a moon far from the sun, heated not by sunlight but by tidal forces from Neptune. All of these discoveries, images, and data from 4 giant planets and their moons revolutionized planetary science. Before Voyager, the outer solar system was largely unknown. We had fuzzy images from ground-based telescopes and a few close-up views from Pioneer 10 and 11. But Voyager gave us the first detailed look at these worlds. It showed us the diversity of the planets and moons. It revealed that the outer solar system is not a cold, dead place, but a dynamic region with active geology, complex atmospheres, and fascinating chemistry. The discoveries from Voyager filled textbooks. They inspired a generation of planetary scientists, and they raised new questions that future missions would attempt to answer. But Voyager's discoveries didn't stop when it left the planets. As it traveled through the outer solar system and into interstellar space, it continued to gather data. It measured the solar wind, the stream of particles flowing outward from the sun. It found that the solar wind slows down as it moves away from the sun, eventually reaching a region called the termination shock, where it becomes subsonic. This transition was predicted, but Voyager confirmed it and measured where it occurs. Voyager 1 crossed the termination shock in December 2004 at about 94 AU from the Sun. Voyager 2 crossed in August 2007 at about 84 AU. The fact that these distances are different tells us that the heliosphere isn't perfectly spherical. It's asymmetric, shaped by the interstellar medium pushing against it. Beyond the termination shock is the heliosheath, a region where the solar wind has slowed but is still present, mixing turbulently with the interstellar medium. Voyager traveled through the heliosheath for several years, measuring the changing conditions. Then came the heliopause, the boundary where the solar wind pressure equals the pressure of the interstellar medium. Voyager 1 crossed in August 2012. Voyager 2 crossed in November 2018. At the heliopause, the solar wind particle density dropped nearly to zero. The cosmic ray intensity increased. The magnetic field changed direction. These were the unmistakable signs of entering interstellar space. Since then, Voyager has been measuring the interstellar medium directly. The particle density, about 0.1 particles per cubic centimeter. The magnetic field, about 5.5 microgauss. The cosmic ray intensity, higher than inside the heliosphere. The temperature of the plasma, about 30,000 Kelvin. Hot by everyday standards, but this is a plasma, not a gas. The individual particles have high energies, which translates to a high temperature, but the density is so low that the total thermal energy is tiny. You wouldn't feel heat if you were in the interstellar medium. There aren't enough particles hitting you to transfer significant energy. These measurements are unique. No other spacecraft has crossed the heliopause. New horizons might eventually, decades from now, but for now, Voyager 1 and 2 are the only probes in interstellar space. They're our eyes and ears in a region we can't observe any other way. Telescopes can study interstellar space indirectly by looking at how starlight passes through it, how the light is absorbed and scattered. But direct measurements, actually being there and sampling the environment, provide information you can't get from remote observations. The exact particle, composition, the fluctuations in density and field strength, the detailed properties of the plasma. This data helps us understand the structure of the local interstellar medium and how it interacts with the heliosphere. Now, let's compare Voyager's distance to other cosmic distances to get perspective. Voyager is 24 billion kilometers from the Sun. The nearest star, Proxima Centauri, is about 40 trillion kilometers away. That's 40 with 12 zeros. Voyager has traveled about 0.06% of the distance to the nearest star, less than 1/10%. Voyager has been traveling for nearly 50 years, and it's covered less than 1/10% of the distance to the nearest star. At its current speed, it would take about 73,000 more years to reach Proxima Centauri. And even then, it would just fly past. It wouldn't slow down. It wouldn't stop. It would zip through the Proxima Centauri system at 17 kilometers per second and continue on into the galaxy beyond. The center of the Milky Way galaxy is about 250,000 trillion kilometers away. That's a 2.5 with 17 zeros. Voyager has traveled about 0.00001% of the distance to the galactic center, 100,000th of 1%. The galaxy is so vast that even decades of travel at interstellar speeds barely register as distance on the galactic scale. Voyager will orbit the galaxy along with the Sun and all the other stars, but it will never approach the galactic center in any meaningful sense. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 24 quintillion kilometers away. That's 24 with 18 zeros. Voyager would need about 40 billion years to reach Andromeda at its current speed. 40 billion years. The universe is only about 14 billion years old. Voyager would need nearly 3 times the current age of the universe to reach Andromeda. And that's the nearest large galaxy. There are galaxies billions of light years away. Voyager will never leave the Milky Way. It will never even leave the local neighborhood of the Milky Way. It will drift among the nearby stars, a tiny speck in a galaxy containing hundreds of billions of stars. This comparison shows the scale of the universe. Voyager's journey, impressive by human standards, is nothing on cosmic scales. The distances between stars are so vast that even our fastest spacecraft are effectively stationary. It would take revolutionary new propulsion technologies, traveling at significant fractions of the speed of light, to make interstellar travel feasible. And even then, the travel times would be measured in decades or centuries for nearby stars. For distant stars, for other galaxies, the times become prohibitive. Unless we discover physics we don't know about, faster than light travel or wormholes or some other exotic phenomenon, the universe beyond. Our immediate stellar neighborhood is effectively unreachable, but that doesn't diminish Voyager's achievement. Voyager was never meant to reach other stars. It was meant to explore the outer planets, and it succeeded brilliantly. The fact that it's still operating, still exploring, still sending data from interstellar space is a bonus, an unexpected gift. Voyager is doing science no one planned for. It's teaching us about a region of space we barely knew existed when the mission launched. And it's doing it with hardware from the 1970s, with computing power less than a modern calculator, with instruments designed and built before personal computers existed. The engineers who designed Voyager couldn't have imagined what we'd be using it for today, but they built it well enough that it's still functioning, still useful, still relevant. The future of Voyager is limited by power. The RTGs decay over time. Every year they produce less power. NASA has been managing this decline by shutting down instruments to conserve energy. The cameras were shut down in 1990 after the Neptune encounter. They're not needed anymore, and they drew significant power. Heaters have been turned off. Non-essential systems have been powered down. The spacecraft is running on the bare minimum needed to operate the remaining science instruments and communicate with Earth. But even with these measures, the power continues to decline. Current projections suggest Voyager will have enough power to operate at least one science instrument until sometime between 2025 and 2030. After that, there won't be enough power to run any instruments. The spacecraft might still have enough power to run the transmitter for a few more years, sending back a carrier signal with no data, just a tone confirming the spacecraft is still alive. But eventually, probably by the mid-2030s, the power will drop below even that threshold. Voyager will fall silent. The transmitter will shut down. The last signal will be sent, and Earth will hear nothing more. When that happens, Voyager won't die exactly. The spacecraft will still exist. It will still be out there, coasting through space, but it will be dead in the sense that it's no longer functioning. No power, no communication, no data collection, just a dark, cold, inert object drifting through the galaxy. The temperatures inside the spacecraft will drop to match the temperature of space, about 3 Kelvin. Everything will freeze. The electronics, the instruments, the fuel lines, the structure itself. Voyager will become a frozen artifact, a relic from the early days of space exploration, but the golden record will survive. Gold doesn't decay. It doesn't corrode in space. There's no oxygen, no water, nothing to attack it chemically. The record will remain pristine for billions of years. The sounds and images of Earth preserved in grooves on a metal disc, protected by its aluminum cover. If an alien civilization ever finds Voyager, millions or billions of years in the future, the record will still be playable. The information will still be there. The greetings, the music, the images, a snapshot of Earth from 1977, a message from a species that might not exist anymore by the time the record is found. Think about that for a moment. Long after humans are gone, long after Earth is gone, consumed by the sun's expansion into a red giant, Voyager will still be out there, drifting, the record intact, the images and sounds preserved, a testament to a species that looked up at the stars and wondered. that built machines to explore, that reached out across the cosmos to say hello. Even if no one ever finds it, even if the record is never played, it's still meaningful. It's a gesture, an act of hope and optimism, a statement that we existed, we mattered, and we tried to connect with the universe beyond our world. There's poetry in Voyager's journey. A tiny spacecraft built by humans, traveling farther from home than anything we've ever created, carrying our music, our voices, our images into the darkness, moving at a speed that seems fast to us, but is glacially slow on cosmic scales, destined to drift through the galaxy essentially forever, a silent emissary from a small blue planet orbiting an ordinary yellow star. Voyager is humanity reaching beyond itself. It's our ambition and curiosity made physical. It's the dream of exploration distilled into metal and electronics and launched into space. Every day, Voyager sets a new record. Farthest human-made object, most distant spacecraft. Every second, it's farther from Earth than any human creation has ever been. This record will likely stand for decades, maybe longer, until we build something faster, something designed specifically for interstellar travel. Voyager will hold the title, and even when something surpasses it, Voyager will still be out there, still traveling, still carrying the golden record, still representing humanity to the cosmos. The distance Voyager has traveled, 24 billion kilometers and counting, is more than a number. It's a measure of human achievement. It represents decades of work, billions of dollars, thousands of people contributing their skills and knowledge to a common goal. It represents the dream that we can leave our planet, explore the solar system, and eventually reach the stars. Voyager hasn't reached the stars. It won't in any human time frame. But it's heading there. It's on its way. And that's what matters. The journey, not the destination. When you look up at the night sky, Voyager is out there. You can't see it. It's too small and too far. But it's there, in the direction of the constellation Ophiuchus for Voyager 1, or Sagittarius for Voyager 2, moving away at 17 kilometers per second, sending back data, measuring the interstellar medium, still functioning after nearly 50 years, still exploring, still teaching us about the universe, and carrying with it a piece of humanity. The golden record, our message to the stars. Understanding how far Voyager has traveled helps us understand our place in the universe. We're on a small planet in a vast solar system, in an enormous galaxy, in an incomprehensibly large universe. The distances are so great that they dwarf human experience. Even our most ambitious exploration efforts like Voyager barely register on cosmic scales. But that doesn't make the effort meaningless. It makes it remarkable. We're small, but we're capable. We're limited, but we're curious. We can't cross the galaxy, but we can send a piece of ourselves into it. And we can dream about the day when future generations might follow Voyager's path, traveling faster, reaching farther, exploring the stars that Voyager can only drift past. Voyager's journey is a journey of discovery. Discovery about the solar system, discovery about interstellar space, discovery about what we can accomplish when we try. Every kilometer Voyager travels is a kilometer of human accomplishment, Every piece of data it sends back is a contribution to human knowledge. Every year it continues operating is a testament to the engineers who built it and the scientists who operate it. Voyager is more than a spacecraft. It's an achievement, a legacy, a symbol of exploration and curiosity. And it will continue that role long after it falls silent, drifting through the galaxy, carrying humanity's message to the stars. The engineering behind Voyager's longevity is worth examining in detail. When the spacecraft were designed in the early 1970s, reliability was paramount. NASA knew the mission would last at least 5 years, the time needed to reach Jupiter and Saturn. They knew the spacecraft would have to function in harsh environments, radiation from Jupiter's magnetosphere, temperature extremes ranging from the intense sunlight near Earth to the cold darkness beyond Saturn, micrometeorite impacts, cosmic rays. All of these could damage or destroy delicate electronics. So every component was over-engineered. Every system had redundancy. If something failed, a backup system could take over. The computers on Voyager are incredibly primitive by modern standards. Each spacecraft has 3 main computer systems. The Computer Command System, which handles commands from Earth and manages the spacecraft's operations. The Flight Data System, which formats data from the instruments and prepares it for transmission. And the Attitude and Articulation Control System, which handles the spacecraft's orientation and pointing. These computers have a combined memory of about 68 kilobytes. 68 kilobytes. Your smartphone probably has 1 million times more memory. A single high-resolution photo from a modern camera is larger than Voyager's entire memory capacity. Yet, these computers have been running continuously for nearly 50 years. No crashes, no reboots, no software updates that break things. Just steady, reliable operation year after year after year. The software on Voyager has been updated over the mission lifetime. Commands sent from Earth can modify the software, changing how the spacecraft operates. This has been crucial as the mission evolved. Software written for planetary flybys isn't optimal for cruising through interstellar space. NASA engineers have rewritten parts of the code, optimized operations, fixed bugs, all by sending commands across billions of kilometers. It's like doing remote tech support, except the customer is 22 light hours away, and if you make a mistake, you won't know for nearly 2 days. And you can't just reboot the system if something goes wrong. If Voyager stops responding, there's no reset button, no way to physically access the spacecraft. You have to solve the problem remotely, using only the information available from previous transmissions. This has happened several times. Instruments have failed. Systems have malfunctioned. In 2010, Voyager 2 started sending corrupted data. The problem was traced to a bit flip in the flight data system, a single bit in memory that changed from 0 to 1, probably due to a cosmic ray impact. This 1-bit error caused the entire data formatting system to malfunction. Engineers diagnosed the problem, figured out which bit was flipped, and sent commands to reset it. The fix worked. Voyager 2 resumed sending good data, 1 bit out of millions. One cosmic ray hit at just the wrong spot, and the engineers found it and fixed it from 4 billion kilometers away. The power system on Voyager is elegant in its simplicity. radioisotope thermoelectric generators. Plutonium-238 decays, releasing alpha particles and heat. The heat flows through thermocouples, devices that convert a temperature difference into electricity. No moving parts, no solar panels that degrade or get covered with dust. Just steady, reliable power generation driven by radioactive decay. The plutonium has a half-life of 88 years, so it decays slowly. After nearly 50 years, about 40% of the original plutonium has decayed. The remaining 60% continues to generate heat, though less than originally. The thermocouples have also degraded over time, becoming less efficient at converting heat to electricity. The combination means power output has dropped from about 470 watts at launch to about 240 watts today. This power decline drives many of the mission's operational decisions: which instruments to run, which heaters to turn on, how often to transmit data. Every watt matters. NASA has been turning off heaters to conserve power, letting parts of the spacecraft get colder than originally designed. Some components are now operating at temperatures they were never tested at. And yet, they keep working. The fuel lines for the attitude control thrusters froze at one point. Engineers thought the thrusters were lost, but they tried pulsing the heaters briefly to warm the lines, and it worked. The fuel thawed enough to flow. The thrusters operated. Another problem solved through clever engineering and deep understanding of the spacecraft systems. The attitude control system is crucial for communication. Voyager has to point its antenna at Earth to transmit and receive signals. Earth moves across Voyager's sky as Earth orbits the Sun. Voyager has to track this motion, adjusting its orientation continuously to keep the antenna pointed correctly. This is done using small thrusters that burn hydrazine fuel. Short pulses, just milliseconds long, that gently rotate the spacecraft. The hydrazine is also slowly depleting. Each thruster firing uses a tiny amount of fuel. After 50 years of continuous attitude adjustments, the fuel level is getting low. NASA estimates there's enough fuel to maintain attitude control through at least 2030. After that, Voyager will lose the ability to point its antenna. Even if there's still power for the transmitter, the signal won't reach Earth because the antenna will be pointing in the wrong direction. The instruments on Voyager are marvels of 1970s technology. The magnetometers measure magnetic fields using simple coils of wire. When magnetic fields pass through the coils, they induce tiny electrical currents that can be measured. The plasma detectors use charged grids to measure the energy and velocity of ions and electrons. The cosmic ray detector uses solid-state sensors that create electrical signals when high-energy particles pass through them. These instruments don't have the sensitivity or resolution of modern detectors. They can't measure subtle variations or fine details. But they're robust. They've been operating in the harsh environment of space for decades. They've survived radiation, temperature extremes, and the gradual degradation of their components. And they're still producing valuable data. One of the challenges of operating Voyager is that Earth's technology has moved on. The computers and software used to communicate with Voyager have been upgraded multiple times. The original systems from the 1970s are long gone, replaced by newer technology. But the new systems have to be compatible with Voyager's old systems. They have to speak the same language, send and receive signals in the same format, operate at the same data rates. It's like trying to run modern software on a computer from the 1970s, or trying to play a cassette tape on a device designed for streaming audio. The formats are incompatible. You need adapters, translators, compatibility layers. NASA has maintained this compatibility through careful engineering and detailed documentation. They know exactly how Voyager's systems work, what commands it understands, what data formats it uses. This knowledge has been passed down from generation to generation of engineers, each learning from their predecessors, each adding to the collective understanding. There's also the issue of institutional memory. The people who designed Voyager are mostly retired or deceased. The engineers who built it, who tested it, who launched it, who operated it during the planetary encounters, many of them are gone. But they left documentation, thick binders of technical manuals, schematics, test results, operational procedures. These documents are invaluable. They contain information that exists nowhere else: how specific systems work, what problems occurred during testing and how they were solved, what the design margins are, how far you can push things before something breaks. Current engineers refer to these documents constantly. They're like ancient scrolls containing wisdom from the past, guidance for operating these aging spacecraft. Let's think about what it means that Voyager is in interstellar space. The term conjures images of emptiness, darkness, the void between stars. And it's true that interstellar space is mostly empty, but it's not completely empty, and it's not static. The interstellar medium has structure, dynamics, evolution. The gas and dust are not uniformly distributed. There are denser regions and less dense regions. There are hot regions where supernova shockwaves have heated the gas to millions of degrees. There are cold regions where the gas is only a few tens of degrees above absolute zero and molecules can form. There are ionized regions where ultraviolet light from massive stars has stripped electrons from atoms. And there are neutral regions where the gas is mostly atomic hydrogen and helium. Voyager is currently passing through the local interstellar cloud, a small cloud of gas embedded in the larger structure of the local bubble. This cloud is relatively dense by interstellar standards, about 0.3 atoms per cubic centimeter, and relatively cool, about 6,000 Kelvin. But even at this density, if you were in the local interstellar cloud, you'd experience it as a perfect vacuum. There's not enough gas to scatter light or transmit sound or affect your motion in any way. Yet, this thin gas has mass. Over vast volumes, it adds up. The local interstellar cloud contains several times the mass of the Sun, spread across a volume tens of light years across. It's part of the raw material that will eventually, millions or billions of years from now, collapse under gravity to form new stars and planets. The magnetic field threading through the interstellar medium is also important. Though weak, about 5 microgauss, this field shapes the flow of charged particles. Cosmic rays, which are mostly protons, spiral around magnetic field lines. They can travel long distances along the field, but have difficulty crossing it. This creates anisotropy, a directionality to the cosmic ray distribution. Voyager measures this. Its cosmic ray detector can determine not just how many cosmic rays are present, but which direction they're coming from. This information tells us about the structure of the magnetic field and the sources of the cosmic rays. Dust in interstellar space is also fascinating. These tiny grains, typically about 1/10 of a micron across, are made of silicates, carbon, or ices. They form in the atmospheres of dying stars, in supernova explosions, in the cold, dense regions of molecular clouds. They're coated with ices, water ice, carbon monoxide ice, ammonia ice, methane ice, depending on the temperature and composition of their environment. And on these icy surfaces, chemistry happens. Atoms and molecules stick to the grain, move around on the surface, react with each other, form new molecules. Complex organic molecules can form this way. Amino acids, sugars, the building blocks of life. These molecules are then released into space when the grain is heated or destroyed, seeding the kaikas, interstellar medium with organic compounds. Voyager doesn't detect these molecules directly. Its instruments aren't designed for that. But the data Voyager sends back about the density and composition of the interstellar medium helps us understand the environment where these processes occur. And future missions might build on Voyager's findings, carrying instruments specifically designed to study interstellar chemistry, to search for complex molecules, to understand how the raw materials for life are created and distributed throughout the galaxy. There's something humbling about Voyager's position in interstellar space. For all of human history, until 2012, everything we'd ever built was within the heliosphere, within the sun's domain. We were children playing in our cosmic backyard, never venturing beyond the fence. Then Voyager crossed that fence. It entered the wider world, the neighborhood beyond our yard, and it sent back word of what it found there. Not alien civilizations or strange new physics, just the thin gas and weak magnetic fields and steady rain of cosmic rays that fill the space between stars. Ordinary interstellar space, but observed directly for the first time, measured by an instrument that was actually there. This is the power of exploration, not to confirm what we expect, though that's valuable too, but to see for ourselves, to measure directly, to remove the uncertainty that comes from remote observation and inference. Voyager told us that the interstellar medium near the Sun is about what we thought it would be. The density, temperature, magnetic field all matched predictions reasonably well. This is important. It validates our understanding of how the interstellar medium works. It gives us confidence that our models are correct, at least for this region of space, and it provides a baseline for future observations. When we send more advanced probes into interstellar space, we'll be able to compare their measurements to Voyager's, seeing how conditions change with distance and direction. The legacy of Voyager extends beyond the data it collects. The mission has inspired generations of scientists and engineers. Many people working in space exploration today were inspired by Voyager's images of Jupiter and Saturn, by the stories of the spacecraft visiting new worlds, by the idea that humans could send machines across the solar system to explore places we'd never seen before. Those childhood inspirations led to careers in science and engineering, to new missions, to continued exploration. Voyager sparked imaginations. It showed what was possible, and it created a culture of exploration that continues today. Voyager also demonstrated that long-duration missions are feasible. Before Voyager, most spacecraft missions lasted months or a few years. Voyager has lasted decades. This changed how mission planners think about spacecraft design and operations. If you build things well enough, if you plan for redundancy and reliability, if you're willing to invest in ongoing operations, you can keep spacecraft running far longer than their nominal mission lifetimes. This philosophy influenced later missions. Cassini operated at Saturn for 13 years, far beyond its original 4-year mission. The Mars rovers Spirit and Opportunity operated for years beyond their 90-day missions. New Horizons continues to explore the Kuiper Belt long after its Pluto flyby. All of these extended missions owe a debt to Voyager for showing that it's possible. There's also a philosophical dimension to Voyager's journey. The spacecraft represents humanity's first physical presence beyond the solar system. For billions of years, Earth was isolated. Life evolved here, confined to this one planet. Then, humans arose, developed technology, and began to explore. First, our immediate surroundings, then the whole planet, then nearby space, the moon, the planets, and now, with Voyager beyond the planets, into the galaxy itself. We've taken our first step into the larger universe. It's a small step. Voyager is only 0.06% of the way to the nearest star. But it's a step, a beginning, and beginnings matter. Voyager also carries a message about who we are as a species. Not just the golden record with its sounds and images, but the spacecraft itself. The fact that we built it, the fact that we sent it, the fact that we maintain contact with it across billions of kilometers. These things say something about us. They say we're curious, we're explorers. We build tools to extend our reach. We value knowledge and discovery. We dream of connecting with something beyond ourselves. Future historians, if they exist, might look back at Voyager as a turning point. The moment when humans stopped being a planet-bound species and became, at least in a small way, a spacefaring species. Of course, that's a generous interpretation. One could also argue that Voyager represents the limits of what we can do. We can send a small probe into interstellar space, but we can't follow it. We can't send humans. We can't establish a presence there. We're stuck on Earth, or at best in near-Earth space for the foreseeable future. The distances are too vast, the energies required too large, the timescales too long. Voyager is as far as we can reach, and it's barely scratched the surface of interstellar space. This interpretation is sobering. It suggests that the universe beyond our solar system might remain forever beyond our grasp. Which interpretation is correct? Both, perhaps. Voyager represents both our capabilities and our limitations, what we can achieve and what we cannot. The tension between ambition and reality, the gap between dreams and physical constraints. We dream of traveling to the stars. We imagine faster-than-light drives, generation ships, suspended animation. We write stories about exploring the galaxy. But the reality is that we can barely send a small probe beyond our own solar system. The gap between fiction and reality is enormous. Voyager sits in that gap, a real achievement that falls far short of our fictional imaginings, but surpasses what previous generations thought possible. Let's also consider Voyager in the context of humanity's future. If we're still around in 1,000 years, Voyager will be a historical artifact, an ancient spacecraft from the early days of space exploration, still drifting through space but no longer functioning, no longer communicating. Future space explorers might encounter it, not intentionally. The chances of anyone finding Voyager in the vastness of space are essentially zero unless they're looking for it specifically. But if they did find it, what would they think? They'd see primitive technology, computers with less power than their wristwatches, instruments that are crude by their standards, communication systems that are laughably slow. They'd marvel that we accomplished anything with such limited tools, but they'd also recognize the achievement that with these primitive tools, we explored the outer solar system, that we sent back images and data that revolutionized our understanding, that we built something that lasted decades and traveled billions of kilometers. They'd understand that Voyager was the best we could do at the time, and they'd appreciate it for what it was. A beginning, the first step on a long journey. Just as we look back at early explorers who crossed oceans in wooden ships, facing storms and starvation and unknown dangers, and we appreciate their courage and determination even though we wouldn't attempt such a voyage with their technology, future explorers might look at Voyager with similar appreciation. Or maybe humanity won't be around in 1,000 years. Maybe we'll destroy ourselves in war or environmental collapse. Maybe we'll face some catastrophe we can't overcome. If that happens, Voyager becomes even more significant. It's one of the few things we've created that will outlast us. Most of what we build, cities and bridges and monuments, will crumble eventually. Rust and erosion and time will erase them. But Voyager is in space. There's nothing to wear it away. No weather, no corrosion, no biological decay. Voyager will drift through the galaxy for billions of years, long after all traces of human civilization on Earth have vanished. If we're gone, Voyager and its golden record will be among the last remaining evidence that we existed. An epitaph written in metal and plutonium, circling the galaxy essentially forever. That's a melancholy thought, but there's also beauty in it, that we created something that will outlast us, that we sent a message to the stars knowing we might not be around to hear a reply, that we reached out into the cosmos with hope and curiosity, not knowing what we'd find, not expecting anything in return, but doing it anyway because it's who we are. Because exploration and curiosity are fundamental to human nature. Because we look up at the stars and we wonder. And we have to know. We have to explore. We have to reach out. It's not optional. It's who we are. Voyager's distance, those 24 billion kilometers, carries all of this weight. Scientific achievement, engineering marvel, philosophical statement, historical milestone, message to the future, symbol of exploration, all contained in a small spacecraft drifting through interstellar space. When we talk about how far Voyager has traveled, we're talking about more than just distance. We're talking about what that distance represents. The decades of work, the thousands of people involved, the knowledge gained, the inspiration provided, the dreams it embodies, the limitations it reveals, the questions it raises about our future and our place in the universe. And Voyager is still going, still traveling. Right now, as you read this, Voyager is moving farther from Earth. In the time it took you to read this script, Voyager traveled hundreds of kilometers farther. Tomorrow, it will be 1.5 million kilometers farther than it is today. Next year, it will be about 550 million kilometers farther. Every second, every minute, every day, the distance grows. The record is extended. The journey continues until the power runs out and the spacecraft falls silent. But even then, the journey won't stop. Voyager will keep moving, keep drifting, keep carrying the golden record deeper into the galaxy, traveling farther than anything humanity has ever created. A testament to what we can achieve when we try, a reminder of how vast the universe is and how small we are within it, and a message of hope that someday, somehow, we might follow Voyager's path and explore the stars ourselves. The comparison between Voyager's journey and human lifespans is striking. Voyager has been traveling for nearly 50 years. That's more than half a typical human lifetime. People who were children when Voyager launched are now approaching retirement age. People who worked on the mission as young engineers are now in their 70s. And Voyager is still out there, still operating, still sending back data. It's outlasted careers, outlasted relationships, outlasted trends and technologies and entire ways of life. The world of 1977, when Voyager launched, is almost unrecognizable compared to today. No internet, no smartphones, no personal computers. The Cold War was ongoing. Disco was popular. The fastest computers were room-sized mainframes with less computing power than a modern calculator. And yet, technology from that era, built with those limitations, is still functioning today, still relevant, still contributing to science. This longevity creates continuity across generations. Older scientists who worked on Voyager during the planetary encounters can collaborate with younger scientists who weren't born until after those encounters. They share the mission, they share the data. The younger scientists learn from the experience of the older ones, and the older scientists gain new perspectives from the younger ones. It's a living tradition, a multi-generational project that bridges time. When the older scientists retire, the younger ones take over. They inherit the mission, the knowledge, the responsibility of maintaining contact with these distant spacecraft. And they'll eventually pass it on to the next generation, until Voyager finally falls silent. There's something profound about a project that spans generations. Most human endeavors are completed within a single lifetime. You build something, you see it finished, you move on. But projects like Voyager don't work that way. No one person can see the whole mission from beginning to end. The people who launched Voyager won't be alive when it finally goes silent. The people who will lose contact with Voyager weren't born when it launched. The mission is bigger than any individual. It belongs to humanity as a whole, to the collective effort across time. This is rare. Most of our projects are individual or single generation. We build for ourselves, for our time. But occasionally, we build something that transcends our own lifetime, something that will outlast us. Voyager is one of those things. The technology on Voyager is also a time capsule of sorts. It represents the state of the art from the 1970s. If you studied the spacecraft systems, you could learn about what technology was available then, what engineers knew, what they valued in design. The redundancy, the simplicity where possible, the careful attention to reliability. These reflect a particular engineering philosophy. They also reflect what was physically possible given the materials, manufacturing techniques, and understanding of the time. Future historians studying Voyager would be studying not just a spacecraft, but a window into the technological capabilities of late 20th century humans. The Golden Record adds another layer to this. It's a time capsule of human culture from 1977. The music, the sounds, the images, they all reflect what the people who created the record thought was important about Earth and humanity. What would you include if you were creating the record today? You'd probably choose different music, different images, different languages. The world has changed. New cultures have emerged. Old ones have evolved. What seemed important or representative in 1977 might seem dated or incomplete today. But that's the nature of time capsules. They capture a moment. They can't be updated. The Voyager Golden Record will forever represent 1977. It will never reflect the Earth of 2000 or 2050 or 2100. It's frozen in time, carrying a snapshot of one moment in human history out into the galaxy. This raises interesting questions about representation. Who decides? What represents humanity? Who chooses the music, the images, the messages? For Voyager, it was a committee led by Carl Sagan. They did their best to represent the diversity of human culture, to include music and sounds and images from different parts of the world, different traditions, different perspectives. But they were limited by the record's capacity, limited by their own knowledge and biases, limited by the technology available to encode and store the information. The record they created is remarkable, but it's not comprehensive. It can't be. No single record could capture all of human culture. So the Voyager record is partial, selective, a curated selection rather than a complete representation. And that's okay. It's what they could do with what they had. And it's more than had been done before. If an alien civilization ever finds Voyager and plays the record, what will they make of it? Will they understand the music? Music is a human universal. All human cultures have music. But would aliens have music? Would they have hearing? Would they process sound in ways that make rhythm and melody meaningful? We don't know. The sounds of earth, thunder and wind and animals, would these mean anything to beings from another world? The images showing humans and landscapes and cities, would aliens understand what they're seeing? Do they have vision? Do they process images the way we do? The mathematical and scientific information encoded on the record might be the most universally understandable parts. Mathematics and physics should be the same throughout the universe, but even that assumes aliens think in ways compatible with how we think. The odds of the record ever being found and understood are vanishingly small. But the attempt is meaningful. We tried. We reached out. We said, "Here we are. This is us. This is our world." Even if no one ever hears the message, the act of sending it matters. It says something about human nature, our desire to connect, our hope that we're not alone, our belief that communication across vast differences is possible. These are human values, human hopes, and they're embodied in the golden record. The distance Voyager has traveled also invites us to think about scale and perspective. From Earth's surface, we look up and see stars, points of light scattered across the night sky. Some are nearby, relatively speaking. Some are far away, but they all look similar. Points of light. We have to use telescopes and instruments to measure their distances, to understand their true natures. From Voyager's perspective, looking back, Earth is a point of light, a pale blue dot, in Carl Sagan's famous phrase. When Voyager was beyond Neptune, at about 6 billion kilometers from Earth, it turned its cameras back and took a picture. Earth appeared as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. That image, the pale blue dot, became iconic. It showed our planet as it really is from a cosmic perspective. Small, fragile, alone in the darkness. Everything that has ever happened, every human life, every civilization, every triumph and tragedy, all confined to that tiny speck. That perspective is humbling. It makes our differences seem trivial. The borders we draw, the conflicts we fight, the things we argue about. From that distance, they all vanish. There's just one small world, one humanity, all sharing the same fate. Voyager gave us that perspective. And now, at 24 billion kilometers away, Voyager is 4 times farther from Earth than when that picture was taken. From Voyager's current location, Earth would be even smaller, even fainter, even more insignificant, a point of light lost in the stars. Thank you for exploring Voyager's journey with me. If you found this fascinating, a like or subscribe really helps the channel keep making these deep explorations of space. And remember, Voyager is still out there right now, still traveling, still sending back data from farther away than any human creation has ever reached. The distance keeps growing, the journey continues, and we're lucky enough to witness it. Good night, and may you never look at distance the same way again.